Right, good afternoon. Welcome back to Math and Modeling Methods. And today will be our last lecture before the deadline or the due date for assignment number 3. So we will finish up today the discussion on solution of cylindrical coordinate system problems. And we'll basically go over an overview of the different combinations of different coordinates and different types of boundary conditions that you can encounter on a cylindrical coordinate system problem, because depending on what coordinates are homogeneous, or depending on what direction is homogeneous or non-homogeneous, then the solution takes on a completely different form, and the solution process actually takes on a completely different approach. So, and as I said, with these we will finish our discussion on cylindrical coordinate systems, and or basically solutions of PDEs in cylindrical coordinate systems, or in particular separation of variables and superposition, which is the technique of choice that we've elected or have been covering. And then when we get back after Thanksgiving, we only have one lecture left, and during that lecture we'll introduce some concept of spherical coordinate systems, or solutions of PDEs and spherical coordinate systems, and talk about how superposition and separation of variables work in spherical coordinate system, and go over an overview of what to expect for exam number 3. Exam number 3 will take place on Thursday, December 3rd. That will be the live version, or the in-class version of the exam, and then that day I'll give you also a take-home exam, which will bring to me the following Monday. That would be the 7th of December. All right, so will be lecture 24, I think. Yes. Right, so now consider Axi-Symmetric Problems. That is when the temperature is not a function of theta, right? So let's, for now, let the temperature, which is a function of R and Z, be R of R and Z of Z. Okay, we're still on steady problems, and now let's assume that we have problems that are functions of R and Z only. So let's again talk about the conduction equation, or the Laplace equation, which in the R and Z direction will be 1 over R d dr R dt dr plus the second derivative of t with respect to z squared is equal to 0. That's the governing equation that we'll be looking at. And after introduction of these assumptions, the separation of variables, the resulting governing equation will look like this. Okay? And now the variables are efficiently or effectively separated. R on one side, Z on another side. And as we always do, we break this up into a separation constant, because the argument is, as always, that if whatever's on the left is a function of R and whatever's on the right is a function of Z, the only way that they can be equal to each other is if both are simply a constant. Now we select the sign of the constant based on the direction of orthogonality, right? Now we're looking at a problem in the R and Z direction. So we're looking at a problem in cylindrical coordinate systems, where again looks like that. And this would be y, this will be x, and this will be the coordinate r, and this will be the coordinate theta. I'm sorry, so theta would be actually in this direction, from the coordinate with respect to x. Not this. All right, so we have case 1. If C direction is homogeneous, that means that both conditions in the Z direction at Z equals 0 and Z equal L are homogeneous, whether they're first kind, second kind, or third kind. Then you select plus lambda squared, you select the positive side, the positive separation constant, so that the eigenvalue problem results in the Z direction. In case number 2, if the R direction is homogeneous, then you select the negative separation constant so that the eigenvalue problem results in the R direction. Now, as you can see, the equation that will result in the Z direction will be the standard sine and cosine equation. The equation that will result in the R direction will be the standard Bessel equation. Okay, so depending on whether the direction homogeneous, the homogeneous direction is R on Z, you select the sign of the constant. All right, so case 1. C direction is homogeneous. Basically, the equation in the C direction will be C double prime of Z plus lambda square of Z is equal to 0, resulting in C of Z equals A cosine lambda and Z plus B sine of lambda and Z such that lambda n are the eigenvalues. All right, so you have this equation plus homogeneous boundary conditions. Homogeneous boundary conditions. So depending on the combination of boundary conditions, again, the case in the table will dictate whether the function that survives is the sine, the cosine, or a combination of the two, whether the eigenvalues are pi n over L, or 2 pi and 2n plus 1 over 2L's, or a combination thereof. Okay, we've done this several times. And in the R direction, the equation that we will end up with is R squared, R double prime of R, plus R prime of R, minus lambda n squared, R squared, R of R is equal to 0. And as you can see, because of that minus sign here, this is the modified, the standard, but the modified Bessel equation, of order 0. There's no nu in there, so it's order 0. So the solution of this equation is Ci0 lambda n R plus B K0, D, K0 of lambda n R. Remember, these functions look like this. If this is R, I0 looks like this, where this is 1, and K0 looks like this. Therefore, as you can see, K0 is singular, R equals 0. So if cylinder is solid, then D equals 0. So if the geometry of the cylinder is basically a solid cylinder, not a hollow one, D must be 0 because the solution needs to be finite at R equals 0. All right. case 2, in the case where the r direction is homogeneous, the r equation will look like r squared, r double prime of r, plus r prime of r, plus lambda square r square r of r is equal to 0. And this is the Bessel equation. Now with a positive sign, this is the Bessel equation of order 0, which has solutions A J0 lambda r plus B Y0 gamma r okay. And here we can call this lambdas lambda n's, such that the lambda n's are the eigenvalues. These equations, remember, look like this. These functions look like this. This is J0. And this is Y0. So Y0 goes to infinity at r equals 0. J0 goes to 1 at r equals 0. So therefore, if solid cylinder, again, B is equal to 0. Cannot allow the solution to go to infinity. The solution needs to be finite at r equals 0. Therefore, B needs to be 0 to compensate for that. The provided eigenfunction and eigenvalue tables for cylindrical problems, solid and hollow, will dictate Rn of R eigenfunction lambda n eigenvalue and n of lambda n the norm. Okay, so I provide you a table. It's on Canvas. As well as a table for rectangular coordinate system. There's a table where the choice or the combination of boundary conditions will dictate which one of the two will survive. In the case when the cylinder is solid, this one always goes away, so you always end up with J0. But the eigenvalues are different depending on whether the boundary condition is type 1 or type 2 or type 3. And the norm are also different depending on what the kind 1, 2, or 3 of boundary condition. Okay? So, in the z direction, you end up with the usual equation that looks like c double prime of z minus lambda squared. Now we know that it's a lambda n squared. C of z is equal to 0. And therefore that leads to non-eigenvalue or non-eigenfunction solutions, because this is not an eigenvalue problem because of the negative sign. C cosine hyperbolic of lambda nz plus d sine hyperbolic of lambda n. All right. Apply remaining non-homogeneous BC to assemble solution and determine the constants of integration using orthogonality. All right, let's go straight to an example, to exercises. So we have the same problem in R and Z. Laplace of temperature in R and Z is equal to 0. This is steady heat conduction with no generation. And the boundary conditions look like this. The temperature at R equal B, comma Z is equal to 0. So it's homogeneous in the radial direction. The temperature at R, comma 0 is equal to 0. And the temperature at R, comma L is equal to f of R. So essentially we have a cylinder and on the periphery we impose temperature equals 0, so it's first kind boundary condition on the periphery. On the top we impose also a first kind boundary condition equal to 0, and on the bottom we impose a temperature equal to some function of R. Okay, there is no theta dependency. Therefore, this problem is axi-symmetric. Nothing drives the problem in the theta direction. There's nothing, this condition doesn't depend on theta, there's no generation that depends on theta, and therefore the solution is completely axi-symmetric, only depends on R and Z. So we have an equation that looks again like, I'm going to rewrite it, ddr r dtdr plus the second t dz squared is equal to 0, and we're going to let t of r and z be equal to r of r, z of z. Same thing we always do. Once we plug that in here, this will result in r double prime of r over r of r plus 1 over r prime of r of r is equal to minus z double prime of z, z of z. And we separate this into minus lambda squared. We want a negative lambda because we want to form an eigenvalue problem in the r direction, because r is the homogeneous direction. So the r problem looks like r squared, r double prime of r plus r prime of r plus lambda squared, r squared, r of r is equal to 0. And since the condition in the r direction is homogeneous, we can say such that r at b is equal to 0. We only have one condition because the cylinder is solid, but we can establish also that r at 0 must be finite. That's a given. The solution of this equation, r of r is equal to a j0 of lambda r plus b y0 of lambda r. This is the Bessel equation of order 0, and therefore the solution is in terms of Bessel functions of order 0. such that R at 0 must be finite, therefore B must be equal to 0. And R at B is equal to 0, therefore 0 is equal to A times J0 of lambda B. A cannot be 0 because if A is 0, B is already 0. If A is 0, then the solution is trivial. So J0 of lambda B must be the one that goes to 0. And that would occur because J0, remember, is an oscillative function that crosses the x-axis or the r-axis in this case infinite number of times. So lambda n equals to the zeros of the Bessel function of order 0. It's the nth zero or the nth root of this function divided by b. These are the eigenvalues. And the eigenfunctions is simply J0 of lambda n r. We don't worry about the constant because that constant will get absorbed by another constant when we assemble the solution together, the r and the z, into the big summation. This is the eigenfunction. Or actually functions, because for every value of lambda n, the function looks completely different. Okay, has more frequency. Okay, so what we're left with is a problem in the z direction that is very standard. S double prime or z double prime of z minus lambda n squared z of z is equal to 0. And we only have one homogeneous condition. Oh, by the way, when I drew this, I drew it the other way around. This the condition at z equals 0 is the one that is 0. So this is 0. And the condition up here is f of r at z equal L. So the homogeneous condition occurs down here according to what is given to us. So we can only use the homogeneous condition, which is z at 0 is equal to 0. The solution of this equation, because of the minus sign, is cosine hyperbolic sine hyperbolic. C cosine hyperbolic of lambda n z plus d sine hyperbolic of lambda n z, such that z at 0 is equal to 0 is equal to c times the cosine hyperbolic of 0 plus d times the sine hyperbolic of 0. This is 1, this is 0, and therefore out of these we get that c is equal to 0. So c of z is equal to d times the sine hyperbolic of lambda n z. So the temperature distribution, which is equal to r of r, z of z, is a combination of all possible solutions from n equal 1 to infinity of dn times j0 of lambda n r times the sine hyperbolic of lambda n z. That is the general solution. Now we need to determine the constant of integration, and to do that we apply remaining non-homogeneous condition. The one that says that t at r comma L is equal to some function f of r. Some given function. So we draw a hat on top of it to indicate that this is given. So f of r is equal to the summation from n equal 1 to infinity dn j0 lambda n r sine hyperbolic of lambda n L. Okay? So we know that the Bessel functions are orthogonal to each other with respect to a weighting function equal to r. So J0 lambda nr is orthogonal with respect to a weighting function of r. So we need to multiply both sides by, so we say fr, and then we multiply both sides by lambda m r times r is equal to the summation from n equal 1 to infinity. This is what we've done all along, times j0 of lambda m r times the sine hyperbolic, and I forgot the r, I'll write it at the end, lambda n L times r. So we multiply each side, or both sides, by j0 lambda m r. Now we integrate from 0 to b. In the r direction, the domain goes from 0 to b. F of r, j0 of lambda m r dr is equal to the summation from n equal 1 to infinity. We can leave the dn outside. We can leave the sine hyperbolic of lambda n L outside and integrate whatever is a function of r, which is j0 of lambda n r, j0 of lambda m r dr. All right? So we know that this function is orthogonal, so that this integral is either equal to 0 if n is different than m, and is equal to n of lambda n if n is equal to m. And that's from the table. So the fact that it's always 0 means that all of the terms in the summation disappear except when n is equal to m. And therefore we can just solve for dm, right? And so that essentially means that this is the integral from 0 to b f hat of r j0 of lambda m r dr is equal to dm, that's the only one that survives that summation, sine hyperbolic of lambda m L times n of lambda m. Switch from m to n, and we'll have dn is equal to 1 over sine hyperbolic of lambda n L times the norm of lambda n times the integral from 0 to b of f r j0 of lambda n r dr. And that is what constitutes now the particular solution. So particular solution. Whatever that function f of r is, then we can just solve that integral. For for this particular case, where boundary condition in R direction is first kind, that means that R of B is equal to 0. N of lambda n is the integral from 0 to b of R J0 square of lambda n R dr, which is equal to b squared times J0 prime of lambda n b squared from table. Of solid cylinder. Solid cylinder. And this boundary condition is first kind. So essentially the solution can be visualized as a 2D problem like this, where R can be shown in that direction, Z can be shown in this direction as the axis of rotation, So, and the geometry is simply a rectangle that goes from 0 to L and from 0 to B. The temperature here is equal to 0, the temperature here is equal to 0, and the temperature here is equal to some function of R. This is an axi-symmetric solution. Alright, so although it looks like a rectangle, it's not a Cartesian problem because the equation is different. The equation obviously looks different than the Laplace equation in Cartesian coordinates. The equation looks like this. If this was a rectangle in Cartesian coordinates where this is x and this is y, then the equation would just look like that. Without these r and this r. All right. So moving along, what happens when we have 3D problems? Consider 3D steady problems. Now the temperature is a function of R, theta, and Z. This is full cylindrical. Now we have different cases. Case 1, theta and Z are homogeneous, and R is non-homogeneous. Let's say that the non-homogeneous condition is applied in the R direction. Remember, we're still doing separation of variables, so we can only afford one non-homogeneous condition. If there's more than one, we need to do superposition and just basically construct multiple problems where each has only one non-homogeneous boundary condition. So now we let the temperature of R, theta, and Z equals to R of R, theta of theta, Z of Z. This will result in an equation that looks like R double prime of R of R. We're still talking about the heat conduction problem. 1 over R prime of R of R, plus 1 over R squared, theta double prime of theta, theta of theta, is equal to minus C double prime of Z, Z of Z. Now because the Z direction is homogeneous, we break this up with a positive separation constant, so that the z problem results in z double prime of z plus lambda squared z of z equals 0 plus homogeneous BCs at z equals 0 and z equal L. So this will result in Zn of z. Remember, sines or cosines, sine or cosine, eigenvalues. Lambda and eigenvectors, eigenfunctions. These are the eigenfunctions. This is the eigenvalues. And n of lambda n the norm. So we go to the rectangular table. Okay? Depending on the combination of these boundary conditions, first kind, second kind, so on. We pick this information up from the table. We don't need to solve that problem. We know it's going to be a sine or a cosine. We know that the lambdas are going to be n pi over L or so. And we know that the norm is going to be 2 over L or something like. Okay? So now the problem we end up with is r double prime of r of r, plus 1 over r prime of r over r, minus lambda n, and actually I'm going to multiply here by r squared, I'm going to multiply this by r squared, and then I'm going to have a minus lambda n square r squared is equal to minus theta double prime of theta, theta of theta, and we separate this with a constant nu square, which we make positive also because we need an eigenvalue problem in the theta direction that's also a homogeneous direction. Okay? So, the theta problem will be theta double prime of theta plus nu square theta of theta is equal to 0 plus either periodicity, we've done this before, or homogeneous boundary conditions on wedge, section of a cylinder, right? If this were to be the section of a cylinder from theta 1 to theta 2. Theta 1 to theta 2. All right? So, theta of theta will be equal to c cosine of nu m theta plus d sine of nu m theta. Such that nu m is equal to m, which is equal to 0, 1, all the way to infinity, if full circle, or not, if this is a section of a circle. All right? And in the r direction, the last remaining direction, we have r double prime of r times r squared plus r times r prime of r, and then we have minus lambda n square r squared plus nu m square r of r is equal to 0. And that is the modified Bessel equation of order nu m. And the result, or the solution of this equation, is E times I nu m of lambda n r plus f times y, I'm sorry, k, this is a k, nu m of lambda n r. I and k, the modified Bessel functions of order nu. All right. Assemble solution. T of r, theta, and z is equal to r of r, theta of theta, z of z, and apply remaining non-homogeneous BC. To find the constant of integration to orthogonality. Same thing we always do. Obviously, slightly more complicated in this case because the solution will be double summation from n equal 1 to infinity, from m equal 1 to infinity, and the constant of integration, let's call it C and m, times r of r, theta of theta, and whatever z n. This is m, this is c n of z. These are the eigenfunctions. All right. So again, we're going through this brief overview showing you all the possibilities. One of the questions on the assignment deals with a cylindrical coordinate problem where the combination of boundary conditions is one that you will see in these particular cases. It's a 2D problem, not a 3D problem. All right, that was case 1. Case 2, when the z direction is non-homogeneous, and when the r and theta direction are homogeneous. Here, theta of theta will result in a cosine of lambda n theta plus b sine of, not lambda, nu, or nu n theta. So this is an eigenvalue. R of R, that's an eigenfunction, sorry, is C j of nu n of lambda m r plus d y nu n of lambda m r. This is another eigenfunction. This is n, this is m. And this is m. And the last non-eigenfunction is e cosine hyperbolic of lambda mz plus f sine hyperbolic of lambda mz. Through the same process, such that nu n's are either equal to n, which is equal 0, 1 to infinity, if full circle, or nu n equals not equal to integers if section of circle. That means from theta 1 to theta 2. So if we have a wedge of a cylinder. And the lambda n's or lambda m's from boundary conditions in R direction. All right. And the last possible case for a 3D problem is actually not possible to solve. Well, there's some tricks that can be applied. So case number 3, where we have theta is non-homogeneous and R and Z are homogeneous. And the only way that this is possible is if we have a section of a cylinder. Something like that. So so if this is the R direction, this is the Z direction, and this is the theta direction, this would be theta 1, this would be theta 2. So we have a wedge or a section of a cylinder, whether it's full, solid, or hollow like this. So for this particular problem, no eigenfunction expansion is possible for these problems. So the only way to find a solution, an analytical solution for this problem, is to use superposition to construct problems where the theta direction is homogeneous and transfer the non-homogeneous conditions to R and Z directions. That is possible under certain circumstances. Okay, so we look at 2D steady problems, 3D steady problems. We know that the process and the solution highly depends on the combination of boundary conditions and also depends on where the non-homogeneous condition is. So it's very important that when you set up the problem, you find and specify where these are occurring, what type you have, and where the non-homogeneous conditions occur. Okay. So, at the beginning of the discussion of cylindrical coordinate systems problems, we look at the general problem where we have full dependency on space and time, R, theta, Z, and T. And we expanded that in terms of eigenfunctions, expansions. We said that, well, if we are to apply separation of variables, we are only allowed to have a non-homogeneous initial condition. If the problem is transient, the non-homogeneity should be in time. It should be at the initial condition. All boundary conditions should be homogeneous. And we looked at a general solution process. So what we'll do right now, for the next few minutes, this will be the last thing we'll discuss on cylindrical problems, is just a basic example of a 1D transient problem in the R direction, cylindrical coordinates. So you'll see what the solution looks like, because there is a problem in the homework that looks like that. So transient problems in cylindrical coordinates. All right, so let's look at an example where we have Z, R, and this is going to be a hollow cylinder. Let's say here. Let's say here. Right? Again, this is the theta direction. And that would be the R direction. So in the R direction, we have A and we have B. And in the Z direction, we have 0 and we have L. And we are going to assume that this problem is axi-symmetric. So that means that the temperature is not a function of theta. And it also has symmetry along z-axis. So the problem is not a function of z either. So the resulting problem will be a function of r and t in this particular case. The governing equation is the Laplace of t of r and t equals to 1 over alpha dt of r and t. So we're looking at transient heat conduction or heat diffusion with an initial condition t r and 0 is equal to some function of r. This is given. That's the initial condition. And boundary conditions. Let's say the Q at r equal a is equal to 0. And we'll say that the Q, that's r equal a, Q at r equal b is also equal to 0. So the heat flux on the inner cylinder is equal to 0, so it's insulated inside, and on the outer cylinder it's also insulated. Okay, so for whatever reason this cylinder is insulated everywhere. This can be infinitely long. It really doesn't matter because there's no variability in the z direction. Or it can be infinitely thin. It can also be a membrane. Okay? So this translates into minus k dt dr times the normal vector of r equal a, which is minus 1, is equal to 0. And that ultimately translates into dt dr at r equal a is equal to 0. The derivative of the temperature on the inner cylinder is equal to 0. This one is minus k dt dr at r equal b times the normal vector, which is positive 1, is equal to 0. At r equal b, the normal vector points up, so that's why it's positive in the r direction. So the t dr ultimately, or r equal b, is equal to 0. So again, we're going to let t of r and t be equal to r of r tau of t and when we plug that into the equation, that will result in, well, the equation looks like 1 over r ddr r dt dr of r and t is equal to 1 over alpha dt dt of r and t. We'll do this again step by step. 1 over r ddr of r ddr of r and tau of t is equal to 1 over alpha ddt of r and r tau of t. So that would be tau of t over r times total derivative of r total derivative of r of r is equal to r of r over alpha and total derivative of tau of t. And we call that r prime, we call that tau prime. So this will result in r double prime of r divided by r of r. We divide everything by r and tau, plus 1 over r prime of r of r is equal to 1 over alpha tau prime of t tau of t. So now we separate, this is already separated, and we assign a constant of separation lambda square, and we make it negative for 2 reasons. We want a decaying exponential in time, and we also want an eigenvalue problem in R because it's a homogeneous direction, as separation of variables will only be applicable if that's the case. For initial value problems, separation of variables only applies when the non-homogeneous condition happens at the initial condition, not in the boundary. So the time problem looks like which results in tau of t equals to a times e to the minus alpha lambda squared t. The R problem looks like r double prime of r times r squared plus r prime of r plus r squared lambda squared r of r is equal to 0. So r of r is equal to c j0 of lambda r plus d y0 of lambda r. And the conditions that we have is that the TDR at r equal a is equal to 0, and the TDR at r equal b is also equal to 0. So we need to add that r prime at a is equal to 0, and r prime at b is equal to 0. The 2 derivatives, a and b, are equal to 0. Now in this case we have a hollow cylinder, so d doesn't go to 0. We're not required to eliminate this part of the solution, because we're allowed to have a function that goes to infinity at r equals 0, as that's not part of the domain. Is that clear? Okay. So in order to apply these boundary conditions, we need to differentiate this. So r prime of r is equal to minus c lambda j1 of lambda r minus d lambda y1 of lambda r. The derivatives of the Bessel functions of order 0 are the Bessel functions of order 1. And lambda is just the argument there. So such that we have these conditions. R prime of a is equal to minus C lambda J1 of lambda A minus D lambda Y1 of lambda A is equal to 0. And R prime of B is equal to minus C lambda J1 of lambda B minus D lambda Y1 of lambda B is equal to 0. So there we have two equations to determine C and D, or just one of them, because these are two homogeneous equations. Alright? So from one of these equations we can say, for example, from the first equation we can say that D is equal to minus C times lambda J1 of lambda A divided by Y1 of lambda A. So this helps us put one constant in terms of another. Alright? So, from the other, then we can plug this into the second equation. And then we have minus C lambda J1 lambda B minus C lambda J1 lambda A divided by, hang on a second, this lambda doesn't go here. This is times Y1 of lambda A times lambda Y1 of lambda B is equal to 0. Alright? So we can multiply through. We can take the C as a common factor and multiply 2 by Y1 lambda A, and the lambda will also be a common factor. So what we have is J1 Y1 lambda A times J1 lambda B minus J1 lambda A times Y1 lambda B is equal to 0. So this right here is the implicit equation for eigenvalues, lambda n's. That's what the table will show you. Also shown in table. Table for hollow cylinders with two second kind boundary conditions are R equal A and R equal B will show this implicit equation for the eigenvalues lambda. The roots of that equation are the eigenvalues. So then, back to eigenfunction. R of R is equal to C J0 of lambda R plus D, which looks like minus C J1 of lambda A Y1 of lambda A times Y0 of lambda R. Alright, now we can multiply the whole thing by Y1 and embed that into a constant. This constant we can take out as a common factor and call it E. R of R is equal to E times J0 of lambda R times Y1 of lambda A minus J1 of lambda A times J0 of lambda R. these are the eigenfunctions. Also from table. All right. So now we need to put together this solution. So we assemble the solution T of R and T, which is equal to R of R, tau of T is equal to, well, the summation goes from n equals 0 to infinity, but if you notice, at n equals 0, this y0 will go to infinity, so this one will vanish. This will look like, and the first eigenvalue will be E0 plus summation from n equal 1 to infinity. I'll explain where that E0 comes from. J0 lambda nr y1 lambda na minus j1 lambda na y0 lambda nr times e to the minus alpha lambda n squared t. Now this E0 term comes from the table. This is a special case when you have two second-kind boundary conditions on either side, or second-kind boundary conditions on either side. The eigenfunctions are equal to this when n is greater than 1, equal or greater than 1, and the eigenfunction is equal to 1 when n is equal to 0. Let me write that for you. You'll see that on the table as a special case. So, special case on eigenfunction table for hollow cylinders with R prime of A equals 0 and R prime of B equals 0. Second kind BC on both sides. In this case, that R n of R is equal to either 1 if n is equal to 0, or J0 lambda nr y1 lambda A minus J1 lambda na y0 lambda nr if n is greater or equal than 1. Greater or equal than 1. Okay? So the last step, use initial condition such that T of R and 0 is equal to F of R hat and apply orthogonality to determine E0 is equal to 2b squared minus a squared, a and b, and En is equal to 1 over n of lambda n times the integral from 0 to b of R f of R times the eigenvalue. eigenfunction. Such that the norm from tape. And those are all possible combinations of problems in cylindrical coordinates. Okay, so whatever combination you're confronted with on the homework, I don't know if you have had a chance to review the homework, but it's due on Tuesday, right after we come back. And then the homework or the exam, either the in-class exam or the take-home exam, might have a problem in cylindrical coordinate system. You will see one of these combinations. Okay, you should address the problem accordingly. All right. Are there any questions? Yes.
The in-class portion is going to be like the first one, or it's open notes?
Yeah, it's all open notes, but we'll talk about it on Tuesday when we come back. On Tuesday we'll have a short class. I just introduce spherical PDEs and spherical coordinates, see how to address them, and then we talk about the exam, tell you how many problems you'll see, and what's an hour and 15 minutes, open books, open notes, and so on, and then and some more specifics, and then the take home you have 5 days to solve it until Monday night. All right. Okay. So have a great Thanksgiving. Be safe if you're traveling or if you're staying, and I'll see you next week.